Good day, everyone. For today's experiment, we will discuss experiment 7, conservation of linear momentum. So, the objective of this experiment is to verify the law of conservation of momentum using the groove track and to determine the velocities of two balls A and B before and after collision, and subsequently their momenta before and after collision. So before we proceed on the experiment, let's discuss first what is momentum. So you will get the idea of momentum from this picture. So why are the engines of a supertanker normally cuts off 25 kilometers from the port? So the answer here is because of momentum. All masses that is moving has momentum. And momentum is also associated with inertia. And if you will remember inertia, this is the tendency of an object to resist the change of its motion. So if the object is at rest, so the object resists to move. And if the object is moving, so the property of the mass is to resist to change its condition, which is moving. So that is what we call momentum. Momentum is the property of moving things. It is also called as inertia in motion. And to get the momentum of an object, that you will just get the product of the mass of the object times its velocity. And the symbol for momentum is P. P stands for progress, which is based on Gottfried Wilhelm von Leibniz. It's defined as progress as the quantity of motion with which a body proceeds in a certain direction. So that's why the symbol for momentum is P. So momentum is defined as the product of mass times its velocity, and the unit of momentum is kilogram meter per second. So for this experiment, we will discuss the conservation of momentum. It states that if there is no external forces acting on the system, the total momentum of the system does not change. So it means the total momentum before is just equal to the total momentum after. So let's assume I have a mass 1 which is moving to the right, so that is the velocity. So mass 1 is m1 times its velocity, so we will get now the product of that, and that is now our momentum. And we have to remember, since we multiply the mass to a velocity which is a vector, so therefore momentum is also a vector. So you have to note the direction of the velocity. If it's to the right, it's positive. If it's to the left, it's negative. Since our mass 1 is moving to the right, the velocity of v1 is positive. Now, let's assume we have mass 2 which is moving to the left. So, therefore, to get the momentum of this mass 2, we will just get the product of mass 2 times its velocity, v2. And remember, our object is moving to the left, so therefore, the velocity is negative. So, let's assume these two masses collide to each other. And after collision, they separate in opposite direction. So let's assume their mass doesn't change but their velocity changes. So we have to get their momentum after collision. And to indicate that these velocities are after collision, we will use prime. So we have here v1 prime and v2 prime. So to compute for the momentum of mass 1 after collision, we will also use prime. So that is p1 prime is just equal to the mass 1 times the v1 prime. For mass 2, that is p2 prime is equal to m2 times v2 prime. So based on the conservation of momentum, the total momentum before collision should be the same to the momentum after collision. So before the collision, we will have these momentums, and to get the momentum before collision, we will get the sum of these two momentum of these two masses. So we have P1 plus P2, in which P1 is just equal to M1 V1 plus P M2 V2. Then after collision, so they separate to opposite direction. So that is after collision, we will have P1 prime plus P2 prime is just equal to M1 V1 prime plus M2 V2 prime. And this type of collision is what we call elastic collision, in which in elastic collision, the total momentum is conserved. So it means the momentum before is just equal to the momentum after, and at the same time, also the kinetic energy is also conserved on this system. For the conservation of energy, whatever the energy before should be equal to the energy after collision. So before collision, we have the kinetic energy of K1, so to indicate if for the kinetic energy of mass 1, and K2 for the kinetic energy of mass 2. And the kinetic energy of mass 1 is just equal to 1/2 M1 V1 squared. And the kinetic energy of mass 2 is 1/2 M2 V2 squared. Since we know that the energy before should be equal to energy after, we will just get the sum of these two kinetic energy before, so that is K1 plus K2, so that is 1/2 M1 V1 squared plus 1/2 M2 V2 squared. So this is how to compute the kinetic energy before collision. For after collision, so it's moving on the opposite direction, so we'll have now K1 prime plus, and for mass 2, we will have K2 prime. So to get the kinetic energy after collision, so we will get the sum of this. So K1 prime plus K2 prime is just equal to 1/2 M1 V1 prime square plus 1/2 M2 V2 prime squared. So again, for elastic collision, energy and momentum are conserved. Now, there are different types of elastic collision. So before collision, so it can either be the mass is moving and the M2 is at rest. So after collision, the mass 1 will be at rest while the M2 will be moving with the same direction of the initial velocity of our mass 1. Or it can either be they're moving on the same direction before. So in order these two masses to collide, the velocity of mass 1 should be higher to mass 2. And after collision, the velocity of mass 2 will be greater, or their velocity after collision might be equal. Or can be before collision, the mass 1 is moving while mass 2 is at rest, and after collision, they will be moving in the same direction with different velocities. These are the cases of elastic collision. There is another collision in which, so that is before collision, and after collision, they will stick together. So in this case, we call this as inelastic collision, in which the two masses combine, so mass 1 plus mass 2, and we will only have one velocity, so that is V prime. So this V prime is the velocity of these two masses that sticks together and move in the same direction and the same velocity. So for inelastic collision, the momentum is still conserved, so we will have a momentum before should be equal to momentum after. The total momentum before, P1 plus P2, is just equal to the total momentum of these two combined masses, which is P prime. So the formula of this is M1 V1 plus M2 V2 is equal to the sum of the two masses times V prime, which is the velocity after collision. And this is what we call the perfect or completely inelastic collision, in which the total momentum is conserved, but the total kinetic energy is not conserved in the system because there is an energy loss, and this energy loss can either be in terms of heat or in any form of waste energy. It means the kinetic energy before collision is not the same to the kinetic energy that was converted and used by these two masses after collision. So for this experiment, we will prove the conservation of momentum using elastic collision, in which the condition here, so we have two masses. Mass 1 is moving while mass 2 is at rest, and after collision, these two masses move in the same direction with different velocity. So instead of using boxes, we will use balls. So mass A for the big ball and mass B for the smaller ball. So mass A before collision is moving while mass B is at rest. After collision, they will be moving in the same direction but different velocity. So for this experiment, our problem only is to get the velocity of these masses before and after collision. And the same with our previous experiment, we will use the idea of projectile motion to get the velocity of this. So we will use a groove track. So before collision, we will only have ball A since ball B is at rest. To get the velocity of ball A before collision, we will use a groove track. We will release the ball A at a certain height of this groove track. As we release it, it will move in a projectile motion. So it will have an initial velocity which is VA. And we will measure the height of this and also the range of the ball as it drops to the carbon paper. We will mark it. So we will mark it as XA. So we will get the range of this ball. So we will do this for 3 trials. So that will be X1, X2, and X3 for trial 1, 2, and 3. And we will get the average of that. So to get the average, we will get the sum of the range of these 3 trials in meters, then divided by 3, and that is our XA average. We will get also the time. So to determine the time of our velocity, we have to use the height of the fall, so which is the Y. And to get Y, we will just measure it. So that is, we have to measure this height from the center of the ball to the ground. And we will use this formula to get 1 over t. This is just the same from our previous formula, which is t is equal to square root of 2y over g. So this time, we will use 1 over t, which is just equal to the square root of g over 2y. And remember, g is just equal to 9.8 meter per second squared. Therefore, to get the velocity of our ball A, we will have x average divided by time, or it's just equal to what is x average times 1 over t. It's just the same. So once we get the velocity of our ball A, which is, again, so I said we can get the velocity of ball A by multiplying the average range times 1 over t, and that is average range times 1 over t. And for the ball B, we know the velocity of our ball B is equal to 0. So that will be 0 here. And to get the momentum, so we will just multiply MA times the velocity of our ball A before collision. And for the momentum of our ball B, so that is mass times the velocity of ball B. You have to measure the mass of ball A and ball B to get the momentum. And to get the total momentum, you will just get the sum of these two momentum. For procedure B, so we will release ball A again at the same height as we release it for procedure 1, and we will just place our ball B at the edge of our groove track, so it will be at rest. So once we release our ball A in our groove track, it will collide to our ball B, and they will have velocity. So this is VA prime is the velocity of our ball A, and VB prime is our velocity for our ball B. To get these two velocity, we will again use the idea of projectile motion. So once these two balls collide, they will hit the floor, and we will use again a carbon paper to mark the position of ball A and ball B. The distance of the mark of ball A, we call this as XA prime, while the distance of our ball B from the mark to the edge is XB prime. And we will do this for 3 trials. So that is for trial 1, let's assume that is trial 2, and for trial 3. So you also have to complete table 1 to get the average range for these two balls after collision. So you have to measure for trial 1, for trial 2, and for trial 3. Now, to get the average range after collision of ball A, you will use this formula. And for ball B, you will also use this formula. So for the velocity after collision, so we will use V A prime is just equal to the average range prime times 1 over t. So remember, that is your answer on the red box, times 1 over t. And for the xb prime, that will be the average range of ball B after collision times 1 over t. So that is, you will just multiply your answer on the blue box times the 1 over t. You are done with the velocity. We will now solve for the moment. That is just the product of mass A times m A prime. For momentum of B, that is just a product of mass B times VB prime. And for the total momentum, you will just add these two momentum. And since our idea here, since this is a conservation of energy, the total momentum before should be equal to the total momentum after. And to get the percentage difference, so we will use this formula in which the total momentum minus total momentum after divided by the average absolute times 100. And for this experiment, so once you complete all the table and all the calculation of this experiment, also answer all the questions on page 79 and all the problems on page 80. Okay, so I hope that is clear for this experiment.